It is observable here that there is a spring. Here at the corner of the spring there is a body with a mass m. From Newton's second law of motion we have that F equals the product of mass times acceleration. From here, mass times acceleration equals minus k times x. When you pull this mass, there is a tendency of the spring to go back. You pull away the mass m, and then you leave it, and then there's a tendency to produce oscillation. So we impose the second Newton's second law of motion, and at the right hand side we have the force that tends to bring back the mass to the initial position. So from here we can solve the ordinary differential equation. We divide by the mass, which is different from 0, of course. And at the left hand side we have that the second derivative of the position with respect to time equals minus k divided by m. So this is some constant that characterizes the spring. The second derivative plus k divided by m times x is equal to 0. X double prime plus k divided by m times x is equal to 0. This is a second order homogeneous linear second order ordinary differential equation. And we can write the characteristic equation, which is lambda squared plus k divided by m. We can write this as lambda minus I square root of k divided by m times lambda plus I square root of k divided by m. And we solve equal to 0. Lambda plus is I. The solutions are imaginary numbers. Square root of k divided by m, and lambda minus equals minus I square root of k divided by m. So the general solution, x of t equals a times cos square root of k divided by m plus b sine square root of k divided by m times t. For t is equal to 0, the initial condition is 0. So from here, a is equal to 0, which means that x of t equals b times sine square root of k divided by m times t, where b is the amplitude of the wave and the angular frequency is omega equals square root of k divided by m. From here, we know that the angular frequency is 2 pi divided by the period, and this is k, the square root of this quantity here. I can reverse here the numerator and the denominator, and I get square root m divided by k, t equals 2p square root of m divided by k. This is the period of the oscillation of vibrating spring. The movement of a vibrating spring can be described by an ordinary differential equations. We use the Newton's second law of motion, and we obtain a homogeneous linear second order ODE with constant coefficients. We solve this ODE, and what we get is a wave function. This wave function, where B is the amplitude of the oscillation and T given here is the period of the oscillation of the vibrating spring. It's a classical example from the topic of mechanics in physics.